In this video, we're going to be talking about a technique called Newton's method. Up to this point in time, we've learned how to find the solutions to some types of equations. An example of this would be quadratic equations. We have the quadratic formula to solve those. But in most cases, it's difficult or impossible to construct a formula to find the solutions to a given equation. Some examples would be given here. In these instances, the solutions are often approximated. One technique would be to use a process called Newton's method. Note that the solution or solutions of f of x is equal to 0 are the values of x where the graph of f intersects the x-axis. Suppose that x equals r is the solution that we are seeking. Even if we cannot find the exact value of r, it is usually possible to approximate r by graphing the function f of x and using the intermediate value theorem. As a refresher, a variation of the intermediate value theorem says that if f is a continuous function on the closed interval from a to b, and if f of a and f of b have opposite signs, then there exists some c in the interval a to b such that f of c is equal to 0. Before we explore Newton's method, let's look at a technique that you might have seen already called bisecting intervals. Okay, so in this graph here, we have some function f of x, and we're trying to find the solution to f of x equals 0 on the interval from a to b. And when we're talking about the method of bisecting intervals, what we're going to do is we're going to take the midpoint of the x values a and b, and the midpoint we can find by using the formula a plus b over 2. And so essentially we're just taking the average of these two numbers. So I'm going to go ahead and put a plus b over 2 here. And because in theory we should be given the function formula, what I can do from that point is I can plug in a into my function. And so this would be here f of a. And then I could also plug in f of a plus b over 2 and get the y value there. Now, if one of them is positive and one of them is negative, then I can kind of close in on the solution. So I would take the midpoint now of my two new endpoints. So my midpoint of a and a plus b over 2, and I would calculate that by adding those two things together and then dividing by 2. Even though this is quite an ugly fraction, hopefully you get the idea of how to find that numerical value. So then from here, this would be a plus b over 2 plus a all over 2. And still we can see that if I were to plug in that value into our function, then still f of a would be a negative number, and then this new f of this thing would be a positive number. So I could take the midpoint once again, and then that would be my new negative number. So then I'd want to use these two as my new endpoints, and I can keep kind of taking the midpoint and applying the idea behind the intermediate value theorem until we get an x value that we deem is close enough. So that is the idea behind bisecting intervals. Let's, I'm going to erase this because that's not actually the midpoint. This is the midpoint, but I was illustrating that we could take we could plug that into our function and get the y value for that. And we could keep going and going and going. So let's now talk about Newton's method as an alternative to this, because we didn't actually really use any calculus using the method of bisecting intervals. Okay, so once again, we have a graph of a function, and our goal is to find a root of that function. And here I'm calling that root r. And what we're going to do is we're going to start off by choosing some x value that we think might be a good candidate for our root. So I'm just going to call this x value x1. And notice that I have drawn here the tangent line of the function at x equals x1. So here, this is the tangent line of f at x equals x1. And so because that's the tangent line, I know that the x value where it touches the graph of the function is going to be x1, and the y value would be f of x1. So let's come up with an equation of our tangent line based off this information. So I'm going to use point slope form, or point slope formula. So we have y minus y1 equals m times x minus x1. And I know specifically the ordered pair that we're looking at, so I'm going to go ahead and replace those values here. So that would be y minus f of x1 equals, and then the slope there of our tangent line would be f prime of x1, and then we have x minus x1. Okay, so this is the equation of our tangent line. And notice also that we are taking into consideration where this tangent line is crossing the x-axis, and we are making note of it. And so our tangent line is crossing the x-axis specifically at this point here, and the coordinates of that point we're going to call x2, 0. So another thing that I can do in my equation of my tangent line is I can plug in some other y and x value that fall on that line, and I'm going to choose this ordered pair right here, x2, 0. So let's go ahead and plug those into that equation. So y is going to be 0, and this is going to stay the same. And then x I'm going to replace with x2. So the whole thing that we're doing is, notice that x2 is kind of another x value that has gotten us closer to r. So here's x2 and here's r. And we want to try to create kind of an iterative process like we did with the method of bisecting intervals. So we're looking for some kind of iterative process. And so what I'm going to do now is, in this equation, I'm going to try to solve it for x2 so that I have my next x value. So let's go ahead and do that. I'm going to divide both sides by f prime of x1. And now my new resulting equation is, I will have x2 minus x1 is equal to, the 0 will kind of disappear, and I will have negative f of x1 over f prime of x1. And again, my goal right now is to solve for x2. So if I isolate x2, I get x2 is equal to, I'm going to add x1 to both sides, and I get this lovely formula here. So there is my formula for x sub 2. And if I wanted to then get my next x value, what's going to happen is I'm going to draw a tangent line here at x2, and then here's my tangent line. It's going to look something like that. And then where that tangent line crosses my x-axis here, I'm now going to use that as my next x value, and I'm going to call it x3. And then we're going to do something similar, and then here I'm going to draw another tangent line, and then there that value is going to be x sub 4. And we're going to continue that process of creating these new tangent lines until the place where it crosses the x-axis is close enough to the root that we are looking for. Now, close enough is relative, and typically we'll have some kind of way to determine if our new x value is close enough, and we'll talk a little bit more about that later. But now that I have this stuff here, let me clean up the screen a little bit. Okay, so I have this formula for x sub 2. Now could I come up with a formula for x sub 3? Well, it's going to work in a very similar fashion, and if I were to kind of have repeated that process, then x sub 3 will be based on the value x sub 2. And if I kind of just look at this equation here and use kind of the reasoning that we have, then x sub 3 is going to equal x sub 2 minus f of x sub 2 over f prime of x sub 2. And we could do the same thing for x sub 4 and x sub 5. So let's kind of look at this now. Here's the steps for Newton's method for approximating roots of a function. 1. Choose an initial approximation for x sub 1 as close to a root as possible. And then for n equals 1, 2, and 3, we have this generalized formula here, and we kind of derived that earlier, but x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n, provided that f prime of x sub n does not equal 0. And then our third step is we end our calculations when some kind of termination condition is met. So let's go ahead and take a look at an example so we can kind of utilize these steps. All right, example 1 says use Newton's method to approximate a root of the function f of x equals x cubed minus 3x plus 1 in the closed interval from 1 to 2. Let x sub 1 equal 2, and then find x2, x3, x4, all the way to up x7. Round your x sub n values to 9 decimal places. Okay, so let's just rewrite the formula. I have x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So this is nice because we're given the first x value to use. So I have x sub 1 is equal to 2. Now I'd like to find x sub 2. So if I'm using this generalized formula up above, then x sub 2 is going to equal x sub 1 minus f of x sub 1 over f prime of x sub 1. And we're given x sub 1. We're told that it's equal to 2. So let's plug these in now. I have 2 minus f of 2 over f prime of 2. Okay, so in order for us to be able to simplify this, I need to find the derivative. So I'm going to come off to the side here and do that. I have f prime of x is equal to 3x squared minus 3. Now I can use this formula to evaluate f prime of 2. And we get 9. Notice in my formula, I also need to evaluate f of 2. So let's do that. That would give me 2 cubed minus 3 times 2 plus 1. Okay, so then we have x sub 2 is equal to 2 minus 3 over 9. So that's 2 minus 1/3, which is equal to, let's see, 6 over 3 minus 1/3, which is equal to 5/3. All right, let's go ahead and well, before I move on, notice it says round your x sub n values to 9 decimal places. So why don't I rewrite x sub 2 as a decimal? So 1.666666667. Okay, so there's our x2 value. Now I want to kind of repeat this process because, again, this is an iterative process, and we'd like to now compute x sub 3. All right, so the generalized formula for x sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. And I highly recommend, in the previous page, we derived this formula, and you could derive it every time, but I just recommend that you memorize this formula. Okay, so this is equal to, I'm going to stick to 5/3 so that I don't have to write all of the decimal places, but we have 5/3 minus f of 5/3 over f prime of 5/3. And as you can see, this is kind of a painful process. So I went ahead and I just threw this into my calculator, and assuming that you did this correctly, if I round this to 9 decimal places, this should come out to 1.5486111111. So there's my x3 value, and it continues on. We want to keep doing this until we find x sub 7. This algorithm or algorithmic process is, kind of getting tedious, so I went ahead and I just pasted in the solutions here. And it turns out that if you have a Texas Instruments calculator, you can get these results a lot quicker. Now, before I move on, I want to come up with the generalized formula for this. So, what do I mean by that? Well, I have x sub n plus 1 is equal to x sub n minus, I'm going to go ahead and plug in the generalized x sub n into my f of x formula. So if I do that, then I get x sub n cubed minus 3x sub n plus 1 over, we found our derivative, so this would be 3 times x sub n squared minus 3. So now that I have this generalized formula, let's kind of look below and see what the steps are with our TI calculator. So step 1 says go to the main menu, or main screen, and press 2, then press enter. And the reason that we're pressing 2 is because that is the x1 value that we're using. Then we're going to use the answer button, which I believe is towards the bottom of your calculator, and we're going to type this in specifically. And the reason that we're using the answer key is we're going to press enter after that. And at this point, as you continue to press enter, it'll give you the next iteration of that algorithm. So here's a more detailed view. Let's see what that looks like on the TI calculator. Okay, so it says press 2 and then enter. And notice in the bottom right corner, it has my keystroke history, so you can follow along that way. Now what I'd like to do is I'd like to enter in that expression utilizing the answer button. So I have answer minus. Now I want to use the fraction bar. And then I have answer cubed minus 3 times answer plus 1 over 3 times answer squared minus 3. Okay, so if I press enter, it should give me my next x value, which, remember, x1 is equal to 2, and so x2 should equal this thing here. And now, because this is so useful, if I press enter again, it will give me my x sub 3 value and my x sub 4 value as I just keep continuing to press enter. So this is x sub 5, x sub 6, and x sub 7. Now, notice that between x sub 6 and x sub 7, it gives me the exact same output value because those answers are really, really close, and my calculator only shows me up to 9 decimal places. Now, very quickly, if you calculated x sub 2 and it spit out the answer 5/3, if you want a decimal, the way that you could do that is by going to mode, and then if you scroll down this list here on our options, if your answer is highlighted to auto, it might output a fraction. And if you want the decimal, just go over here and highlight DEC for decimal there, and that should fix your issue. And so, as you can see, if you have a TI calculator, it makes this process a lot easier because after you've typed in that expression, if you just keep pressing enter, it should spit out the next x sub n value. Okay, so coming back here, we have found all the way to x sub 7, which is what it asks for. And again, notice that x sub 6 and x sub 7, because we're only spitting out 9 decimal places, they appear to be the same value. And if I kept pressing enter, it would continue to spit out the same value. So let's go ahead and work on another example. Example 2 says, use Newton's method to approximate the square root of 2, round your final answer to 9 decimal places. Now, this question's a little bit more challenging because of a few different reasons. One of them being we're not given a function, so we need to create our own function, and I'm going to create my function to be f of x is equal to x squared minus 2. And the reason that I'm making my function be this is, notice that if I set x squared minus 2 equal to 0, if I added 2 to both sides, and then I solve for x, I would get x equals plus or minus the square root of 2. So because this function has a root of the square root of 2, now I can utilize this function in my Newton's method formula. So I'm going to go ahead and find the derivative of this function, which is equal to 2x. And now I'm going to write out my generalized formula for x sub n, which was, this should actually be x sub n plus 1, is equal to x sub n minus f of x sub n over f prime of x sub n. And because we have the f and f prime formula, let's go ahead and do this. Okay. And you might be asking, Mr. Kwan, how much work do I need to show if I can just spit everything into my calculator? So I'd like you to show out all of the work that you do, at least for calculating up to x sub 2. After that, it's okay if you just spit out x sub 3, x sub 4, etc. So what do I mean by that? Well, first off, another challenging thing about this question is that we are not given x sub 1, which would be our starting value. So we're trying to approximate the square root of 2. I know that the square root of 2 has to be between the square root of 1 and the square root of 4. I know that square root of 1 is equal to 1, and I know the square root of 4 is equal to 2. So I know it's between 1 and 2. I'm just going to start off with letting x1 equal 2. So let's do that. So x1 is equal to 2, x sub 2. I have my formula. That's going to be x sub 1 minus f of x sub 1 over f prime of x sub 1. Let's fill in. So that'd be 2 minus 2 squared minus 2 over 2 times 2. Okay, so we get 3/2 or 1.5 for x sub 2. And all of this work is necessary if I were asking you this like on a homework question or an exam question. And then for me personally as an instructor, I'm okay with you from here just using your calculator and just spitting out x sub 3. So let's go ahead and do that on our calculator and see what that looks like again for that process. All right, so because my x1 value was 2 in this case, I need to enter in my x1 to start. Now, it's just a coincidence that in the last two examples, our x1 value happens to be 2, so it's not always going to be 2 enter that you plug in. It's just going to be whatever x1 value is to start off with. It's just a coincidence that they both happen to be 2 in the last two examples that we covered. So from here, now I have answer minus fraction. I need the f of x sub n in my numerator. So that was, let's see, answer squared minus 2. And then in my denominator, I need 2 times answer minus 1. And remember, here, answer is supposed to take the place of x sub n, essentially. So now I press enter, and I get 1.333 repeating. Okay, this is such a good illustration of why you should do it by hand, because I know that I made an error here since we got 1.5 when we did it by hand. So I'm going to go ahead and clear everything. And the reason is I wasn't supposed to put that -1 in the denominator. So hopefully you caught that at home as you're watching this. So I'm going to go ahead and clear my screen. And I'm going to press 2, enter, and then hopefully I don't mess it up this time. Okay, so if I did this correctly, it should come out to 1.5, which I did here. Okay, so that's my x sub 2 value. Then if I press enter again, that will give me my x sub 3 value. And notice that there wasn't a stopping condition in this example, or it didn't tell me what x sub n to stop at. So I'm going to continue, and that would give me x sub 4, x sub 5, x sub 6, and notice that I think it's sufficient to stop here because now we get the same answer for x sub 5 and for x sub 6. So let's go back into our notes. All right, so I went ahead and I just copied and pasted our x sub n values. And again, notice that x sub 5 and x sub 6 repeat. So since our last two values gave us the same output value, we can stop here. And finally, we have that the square root of 2 is approximately equal to this decimal here. And that concludes example 2. So it turns out typically Newton's method is used to find roots fairly quickly. However, things can go wrong, and some reasons why Newton's method might fail. One, at one of the approximations x sub n, the derivative f prime of x sub n is equal to 0, but f of x sub n is not equal to 0. As a result, the tangent line of f at x sub n does not intersect the x-axis because it would give you a horizontal tangent line. Therefore, we cannot continue the iterative process. Case 2 is the approximations x sub 1, x sub 2, x sub 3 may approach a different root. If the function f has more than one root, it's possible that our approximations do not approach the one for which we are looking, but approach a different root. This event most often occurs when we do not choose the approximation for x sub 1 close enough to the desired root. So we can see a visualization of case 2 here. So this is the root that we are looking for, and so if we choose our x sub 1 value and we don't choose it carefully enough, if we draw the tangent line, then the x sub 2 value is going to be located right here, and then what's going to happen is we're going to find this root even though that's not the one that we are searching for. And in the last case, case 3, the approximations may fail to approach a root entirely. This might happen because successive approximations continue to alternate or kind of bounce back and forth between the two values. So notice maybe I'm trying to find this root here in case 3, and I might start here, and then if I draw the tangent line, that's going to give me this one, and then if I draw this tangent line, that's going to return me back here, and it's kind of just going to bounce back and forth. So that is a failure of Newton's method and might potentially happen, in which case you might try to choose a different starting x1 value or an entirely different technique altogether. Example 3 says, use Newton's method to approximate the place where the functions f of x equals cosine of x and g of x equals x intersect, and then round our final answer to 9 decimal places. So before we start to do this, I just kind of want to graph what we're doing here. So here's a very rough sketch. Here's my y-axis, here's my x-axis. I know that cosine of 0 is 1, so let's say this is 1, and my cosine graph looks something like that. And then I have the line y equals x, that looks something like that. And we are trying to find the location, the x value, where these two graphs intersect. So again, this is y equals cosine of x, and this is y equals x. And algebraically, how we can find the point of intersection, because I can't really tell off of the graph what that x value is, we can set the functions equal to each other. So I have cosine of x is equal to x. And you might be asking yourself, well, I need a function if I'm going to use Newton's method. So what I can do is I can subtract x from both sides. And now I have an entirely different function altogether. And so even though this was called f of x and this was g of x, so why don't we give this a different name? Maybe I'll call it h of x. And we're trying to essentially solve where is h of x equal to 0, and that will give us the same solution for where these two functions are equal to each other. So let's come up with a formula. Again, I'm just kind of copying down the general one that we should have memorized. In this case, let me change this to h since we called our function h here. Okay, so if this is h of x, then I want to also find h prime of x, which is going to be negative sine of x minus 1. And if I plug in, let's see, I think it might be easier if I factor out a negative 1 here. That's going to give me sine of x plus 1. And so this negative and this negative will change into a plus. So let's do that. Okay, so I have cosine of x sub n minus x sub n over sine of x sub n plus 1. Okay. From here, I need to choose an x1 value, and let's see, where is cosine equal to 0? That's going to help me identify this point here. Cosine is equal to 0 at pi over 2. And so I think starting off with x equals 1 would be a good starting place, since pi over 2, that's approximately 3.14 divided by 2. So I think our solution is going to hover kind of near x equals 1. So then x sub 2 is equal to x sub 1 plus cosine of x sub 1 minus x sub 1 over sine of x sub 1 plus 1. Now, another reason why it's really important in our calculator is when we're plugging in our calculator, this here is going to be an answer, this here is going to be an answer, this here is going to be an answer, this here is going to be an answer. That plus 1 is always going to stay a plus 1, so please be very careful in your calculator. I'm kind of just writing out where the answers are going to be, and then the plus 1 is not an answer, even though it seems like it in this case right here. So x sub 2, if I throw that into my calculator, let's just write that out. That gives me 0.750363868. Okay, so now that I've done all this work to show my calculation for x sub 2, it is sufficient to use your calculator, your graphing calculator, for the remaining calculation. So let's go ahead and do that. Okay, so remember this time around, our x1 value was 1, so I'm going to press 1 and then enter. And then we have second answer, and then we changed the formula because we factored out the negative, so it's going to be plus my fraction bar, then I have cosine of answer minus answer, and then in my denominator I'm going to have sine of answer, and then plus 1. And let's see what that gives us. There we go. So that is the x2 value that I wrote earlier. This would be x3, x4, x5, and x6. So between x5 and x6 is when we get the same output value. So let's go ahead and copy those down into our notes. All right, so using our calculator, we found these x sub n values, and again, x sub 5 and x sub 6 is when they start to repeat. So finally, we have that f of x and g of x intersect when x is approximately this decimal here, and it turns out that the point of intersection, if you wanted to figure out where they intersect, since it's on the line y equals x, the x coordinate and the y coordinate have to be the same, so that is this point of intersection here. So if I called this P, then P would be this point here. And that concludes this video on Newton's method. Thanks for watching.